Okay, so we're looking for the acceleration of the object. Okay, we know that on this graph we have velocity and we have time. Okay, so what this graph is showing me is that the velocity of this object is changing over time. Would you agree? Okay, on any graph, does the slope represent the rate at which y changes in reference to x? It's always that, right? It's y minus b over x. That's what slope is. Okay, it's rise over run. So on this graph, would that slope tell me the rate at which my velocity changes per second? That's the thought process you want to go through. You don't have to memorize it, the accelerations and slope on this kind of graph. You just have to walk yourself through it, okay? And you'll always get to it. That's the skill I want you to have, because then you can apply it to any graph. Okay, so that means then that for 1 mark, the acceleration on this graph is positive 3.28 meters per second squared. Okay, the slope on this graph represents the rate at which velocity changes, and that's acceleration. Okay, what's the initial velocity of this object? Okay, so initial velocity means how fast was I going at time 0. Okay, so how fast was it going?
Negative 6.57.
Exactly. The y-intercept tells me how fast the object was going and in what direction, because it's a velocity time graph, okay, at time 0, and that number happens to be negative 6.57 meters per second. Okay, that's that graphical interpretation stuff. Levi, question? How do I get this? Okay, did you try and do a VF minus VI over T calculation? Okay, that's not going to work. Okay, here's why. The points you use, we don't know the actual values of these points, right? We would have to estimate them. Right? Even if I had the graph, even if I had the actual numbers, okay, this dot, is it on the line? Okay, and this dot is actually pretty squarely on the line, but the line that connects this dot and that dot does not have the same slope as this one. When we have a graph, Google Sheets takes the average of all the points, which is more accurate than taking the last point and the first point and dividing them by time. Does that sort of make sense? Okay. So on a graph like this, I absolutely can't do that because I don't know the values of those dots. If it was an irregular graph like the ones we were working on yesterday, and I said, what's the acceleration during this section? I would know the values. I'd be able to read them, and then it would be appropriate to do that. Does that sort of make sense? Okay. All right, how many people are still working on C? Okay, we're done C, or we're just frustrated with C? It's okay either way. All right, let's have a look at C. So we want to find the displacement of the object between 5 seconds and 20 seconds, right? Yeah. All right, so we're dealing with a 15-second interval, okay, for this part. Now, if I'm looking at this, okay, I know that I've got essentially these two types of motion that I'm going to deal with. Okay? The box, the rectangle, represents how far the car would travel, or whatever this object is, okay, would travel if it just traveled at a constant velocity. That I have to include. Okay? I also have to include how far it travels while it's changing its velocity. That's the triangle above. Okay? So when we're calculating those areas, what we're doing is taking the average velocity and we're multiplying it by time. It just happens to work out that we can go base times height, and base times height divided by 2. Here's the problem. I don't know how high the box is yet. Okay? I also don't know how high the triangle is yet. Can I get those two numbers? Yeah, because their heights are just y values. And I know what time they occur at, 5 seconds and 20 seconds. Right? So all I have to do is plug 5 seconds in for x, and I'll know how high the box is, because that'll tell me how fast the object is going at 5 seconds. Everybody follow me there? Okay? This is one of those like really higher level kind of questions. It's tricky. It makes you do a lot of things. Okay? And then I could use the same logic here. I would plug 20 in for x, and that would give me the height here. But is that the height of the triangle? It's not, okay? I would have to subtract what I calculate here so that I only get the height of the triangle and not all the way down to the x-axis. Everybody follow me there? Just geometry stuff, but it's things we have to watch out for. Okay, so to get that, okay, first calculation we're gonna do, y equals 3.28 times 5 seconds plus negative 6.57 meters per second. Sorry guys, I forgot to fire up the calculator here. Okay, 3.28 times 5 minus 6.57. Okay, so at that point, the velocity is 9.83. Just looking at the graph and kind of eyeballing it, that seems about right. It's a little less than halfway up. Okay, good. All right, so now I know that this height here is 9.83 meters per second. I need to do the same thing here, okay, at 20 seconds. So I'm going to go 3.28, okay, times 20, right, minus 6.57. Okay, so 59.03, that looks about right. The top of the graph is 60, pretty close to the top of the graph. Okay, probably did that right. But that's all the way from the x-axis. I only want the height of the triangle, so I have to subtract 9.83. Okay, 49.2. Now you know why they did all that weird shape stuff, okay, in math. Okay, 49.2 meters per second. Okay, do I have enough information now to calculate those areas? Okay, so I've got 15 seconds on the base for the rectangle, 9.83 meters per second high. So I'll take my 9.83 and I'll multiply it by 15 seconds. Okay, so that box is 147.45 meters. Okay. Now I got to do the area of the triangle, or rather, I'll take this number here and divide it by 2 to get the average velocity during that time, and multiply it by 15. Okay, so 15 times 49.2 divided by 2. Okay, 369. That fits because it's a much bigger area than the little rectangle. So, yep. 369.0. Perfect. Okay, and that is meters. What do I have to do with those two numbers? Add them together. Yep. Okay, and then I've got the total displacement. Okay, so the total displacement for that one is 516.45 meters. Okay, now I'm going to let you in on a little secret. That's the kind of thing that ends up on an exam for this reason. Not because it's hard. It was hard because you'd never seen it. We hadn't done one exactly like that before. That's what made that tricky. But in that question, did I make you analyze the graph? Did I make you do some y equals mx plus b calculating? Did I make you find the displacement on a velocity time graph? Right? Basically, I made you do everything there is to do with a linear velocity time graph that I could ask you. Okay? Was any individual step really taxing for you? I mean, maybe you didn't know which steps to do, but like once I showed them, it's like, oh, I can do y equals mx plus b. I can plug numbers in and do algebra. I can add numbers together. Okay? The trick here is that question is difficult if we're not able to do a good job of interpreting the graph. Okay, and that's what we want to get at. I know I keep harping on that, but that's important. Okay, it's important to be able to analyze a graph and go, oh, I have this. Here's the next step for me. Okay, rather than, oh crap, I memorized I'm supposed to do this, but I don't know how to get there. That can lead to trouble. Okay. All right, for D, how long will it take to reach a velocity of 100 meters? Sorry, I should ask, how many people have done D? How long will it take to reach a velocity of 100 meters per second? What are they asking me for? They're giving me a y. They're asking me for x. How long will it take, right? Okay, so I'm going to take this formula here, and now I'm going to solve for x. Okay, so I'm going to subtract b over to the other side. So I'm going to have 100, that's my y value, minus b, negative 6.57. And then I'm going to divide that by m, 3.28. And that's going to equal x, how long it will take to reach a velocity of 100 meters per second. We've done lots of those calculations already. Okay, so 100 plus 6.57, okay, divided by 3.28. How important is it to do the top before the bottom or enclose the top in brackets? If you want to get the right answer, it's really important. Okay, okay, that's going to take 32.5 seconds. Yeah, that seems pretty reasonable. It takes 20 seconds to go 59 meters. Yeah, that seems like a reasonable answer. Okay, 32.5 seconds. Okay, questions on D? All right. What's the trick with E?
Put into seconds.
Yep, I give it to you in minutes. It can't be in minutes. Your time's in seconds. Okay, so you got to convert it. That kind of dirty trick happens all the time. Okay, we always have to make sure our units are matching. If I say 1 minute, you don't plug 1 in for x, you're going to get a very strange number. Okay, we want to put in 60 for x this time. So it's just a y, solve for a y question again. 3.28 times 60 seconds plus negative 6.57. Okay, so when we plug that one in, okay, so 3.28 times 60 seconds minus 6.57. All right, so 190.23 meters. That seems about right. Sorry, not meters, meters per second. Okay, so those last two are 2-mark questions because basically what you're doing is showing me the graphing equation with the numbers plugged in and an answer. Okay.
With minutes, shouldn't we always convert it since there isn't like a distance unit to match up?
Yeah, we don't usually use meters per minute. Yeah. It actually, the quick answer would be yeah, most of the time. The truly correct answer is you got to look at the graph. If that graph had minutes on the x-axis, you'd leave it that way, right? Because then your units would match. I can't remember ever giving a meters and minutes graph or meters per second and then minutes graph. It doesn't make any sense. Yeah.
For E, do we have to put a positive on our answer?
Yes. Good eye. That should have a positive because it is velocity. Okay. All right. So now that we've seen that question, if I was to give you another one like that, would it be as intimidating? Okay. So that's why that's why we spend so much time on it. So if it feels like I'm just keep giving you more and more graphs, there's always something different on the graph I give you. Okay, and I want you to see some of those other things that could be asked or different ways to ask you to do the things you know how to do. All right. All right. Position versus time graph. This is fairly similar to the one you had on your practice quiz. Okay, so let's have you guys try that one, and then we'll actually look at the practice quiz questions too. Okay, after. All right, so we got a position versus time graph. Let's just quickly kind of go over what the graph is telling us. What's going on in the first 2 seconds? Nothing. Okay, it's a position time graph. It's telling us where the object is. The object is at a position of negative 15 meters for 2 seconds. That means it's staying there. All right, what happens after that? What happens between 2 seconds and 5 seconds? It's moving. Which way?
Up.
Yeah, up, forward, in a positive direction. How? Constant velocity or accelerating? Constant velocity. Okay? Sometimes our gut goes, why going up? Going faster. Not going faster, going farther. Okay? It's a position versus time graph. If it was accelerating, what shape would be on here? right? It'd be a curve, okay? Either an upward curve for speeding up, a flattening curve for slowing down, okay? So, in this case, the object is traveling at a constant velocity during that time. And then, between 5 seconds and 8 seconds, same thing. Where's it going faster? Between 2 and 5 or 5 and 8? 2 and 5, because the line is steeper, okay? The rate at which the position changes is quicker. All right, what's going on between 8 and 10 seconds? Sitting still, yeah, sitting at a position of positive 6 meters. Okay, and then what does it do? Between 10 and 13 seconds. Goes backwards at a constant velocity. Okay, and then what? Then it stops. Okay, so calculate the displacement between 0 and 10 seconds. All right, I can calculate displacement by going average velocity times time, or I can calculate displacement with final position minus initial position. Which would be most appropriate here? Yeah, the second one, final minus initial. That's what's on the graph, okay? I can read position directly off the graph. I don't know what the velocity is because, well, there's a bunch of different velocities on this graph, so that one's out. I can't use that one. That's the process you want to go through. You don't have to memorize, okay? But look at your formula sheet and go, okay, I need to calculate displacement. Displacement's in this formula, okay, I can't use it on that one, I can't use it on that one, but maybe this one. Okay, so between 0 and 10 seconds. All right, so my final position is positive 6 meters. Okay, and my initial position is negative 15 meters. Everybody all right with that? Okay, so 6 minus negative 15 should give me positive 21 meters for a displacement between 0 and 10 seconds. All right, what is the total distance traveled over the whole trip? Can I use this formula for that? Not for the whole thing, but can I use it for the pieces? I can, because I have to know how far this object goes in total, direction not mattering. So if I start down here at negative 15 and I go to positive 6, well, I go 21 meters there. Okay? It doesn't matter that it's different speeds, it's just how far did I go? 21 meters. Okay, and then after that, I stop for a little while, so that doesn't contribute to my distance. Okay, but then I go from positive 6 to negative 3. That's 9 meters. Sorry, I did the final position minus initial position in my head there. Okay, so what's the total distance traveled? 30 meters, yeah. Okay, so yeah, I use the stuff on the formula sheet, okay, but I've also got to know that in terms of distance, I just need to know how far, and add them all together. Okay, okay. Question C. I do this, spoiler alert, on tests all the time in the written response section. Just like this. What is the acceleration between 2 and 5 seconds? What do you suppose people do? Yeah, they go, oh, I can calculate acceleration, Coderre. And then they plug in 0 and 15, and then they divide it by 5 seconds, or by 3 seconds. What's wrong about that? Is velocity on this graph? That's what's wrong about that. I can't use that equation on here. And secondly, there's no what on this graph? There's no curve. We already established that between 2 and 5 seconds, the object was traveling at a constant velocity. What's the tip-off? It's out of 1 mark. If I wanted you to use a formula, I'd make it out of at least 2. At least. Okay? So that's the tip-off. If it's out of 1 mark, you know I always give marks for work. If it's out of 1 mark, there's no work. Okay? It's an interpretation, okay, kind of question. All right, so that one is 0. The object is not accelerating during that time. Now, here's a weird thing. 0 meters per second squared is a correct answer for this, as is just 0. Because technically you can't put units on something that has no value. Okay, so either one of those would be okay. It's all right if you put units on it, because then I get this warm feeling inside that says you remember that units are important and everything should have units. But technically, on a value of 0, you don't have to. Okay. All right, D, what is the average velocity over the whole trip? Okay, what are the ways I can calculate average velocity? I can use y equals mx plus b, but I don't have that here, because it's not a single linear function, okay? But I do have this formula that says that v equals displacement over time, and that is actually average velocity. And I just used this formula a minute ago to calculate displacement. That means I can substitute that into that formula and say that v equals final position minus initial position divided by time. Is that saying the same thing? It is, it's just an expanded version. All right, so over the whole trip, final position, -3. Initial position, -15. Okay, and that took 15 seconds. All right, -3 minus -15 should be +12. Okay, 12 over 15, I think that comes up to 0.8, right? Yeah. Okay, so 0.8 positive meters per second. Okay. Everybody all right with that one? Okay, pretty typical, okay, kind of question. All right, let's have a look at the 2 that I gave you for the practice one. Brace yourself for the loud camera click. Sometimes it startles me. Yeah. Okay, does anybody want a few more minutes to try that one now that you've seen one like that? Maybe that one was troublesome last night. Let's just say, I'm gonna give you about 5 to 10 here. Okay, give this one a try again. Okay, if you got it last night, great, take a little breather. Okay, but if you didn't, okay, give it a try now. It's basically the flip. It's exactly the flip of the one that I gave you. I just put negatives on everything. Okay, so just it's just the flip of what we did. But because it is flipped, there's 1 or 2 small differences. All right, but I'll give you guys a few minutes on that one, and then we'll go over it. All right, so for 1 mark, what's the acceleration of this object?
Oh, is it velocity?
Velocity versus time graph. If it was position, you're totally right.
Minus 3.48.
Minus 3.48 meters per second squared. Okay, it's the slope of the line, because this is a velocity time graph, and it is clearly showing us an object that is changing its velocity at a uniform rate. Okay, what's the initial velocity of this object?
3.75.
Right, 7.75 meters per second in positive direction. Okay, all those little things are important, right? We gotta have all those things on our answer. Okay, so that would be positive 7.75 meters per second, because at time 0, that's exactly how fast it's going. All right. Calculating the displacement between 5 and 20 seconds. Exactly the same as what we did on the other one? Yeah, I've got to find, okay, the size of this box and that triangle. Is it okay that they're upside down? The area will just be
Negative.
negative, yeah, this object's going backwards. All right, so I've got to calculate what's the value of the line, not the point, okay, at 5 seconds. All right, so that's the same calculation we did before. We're going to go y equals negative 3.48 times 5 seconds plus, not times, plus 7.75. Okay, so negative 3.48 times 5 plus 7.75. 5, not 2. Okay, negative 9.65 meters per second. Okay, so negative 9.65 meters per second is the height of that rectangle. Now I need to find the height of the triangle, so I do the same calculation, negative 3.48, but now I substitute in, how much? Somebody whispered it, and it was right. What do I put in for x if I want to find this height? 20, yeah. Okay, times 20 plus 7.75. All right, so negative 3.48 times 20 plus 7.75. Okay, negative 61.85. That looks about right, given where that line falls. Okay, meters per second. Now, is that the height of the triangle? What do I have to do to that number?
Subtract 9.
Exactly. Subtract 9.65, the height of the rectangle, because I only want the height of the triangle. I don't want the distance from the x-axis to the point there. Okay, so I'm going to take that number and I'm going to subtract 9.65. Oh, but not a negative. But I just type it in and not be lazy. Minus 9.65. Whoops, I still did that wrong. Should have been plus because it was a negative number. 61.85 minus 9.65. Okay, 52.2 is the height of my triangle. In meters per second. Okay. All right, do I have now what I need to calculate the area of those boxes? Box and triangle. All right. So for the box here, we're going to have 9.65, negative 9.65 times 15 seconds. Okay, that's average velocity times time. All right, negative 144.75 meters. Okay, and then for the triangle, okay, we're going to take our negative 52.2, okay, and we're going to multiply that by 15 seconds, and then we're going to divide that by 2. All right, negative 391.5. And that's in meters. Okay, and then what do I do with those two numbers? Okay, what do I do with those two numbers? Add them up, exactly. All right, so there's the total displacement, almost exactly the same as the other question I gave you, just negative. Okay, so negative 536.25. And that's in meters. Okay, so we would need both the negative and the meters for that question. Okay, is that making a little more sense? Okay, we always just got to kind of follow those little rules. Okay, analyze the graph. All right, how long would it take to reach a velocity of negative 100 meters per second? Okay, how long always means solve for? Time. Time's on x-axis. All right, so we're solving for an x value. So x equals y minus b over m. The y value they gave us was negative 100. We're going to subtract 7.75, the y-intercept, and divide that by negative 3.48. Okay, if I forget a negative in here, will I know that when I do it? Because it'll tell me I went back in time. Okay, if I forget one of those negatives and I get a negative answer for time, I've definitely done something wrong. Okay, so I'm gonna take the 100, so negative 100 minus 7.75, and then divide that by negative 3.48. Okay, good, I didn't go back in time, okay? I could mess up the timeline, and, butterfly effect and all that, okay? 30.96, negative 30.96 seconds. Why did I put that under a Y? I'm up here. I got lost. 30.96 seconds. Can't be negative. All right. Everybody all right with that? Okay. And does that sort of make sense given where the graph is, right? Like this is negative 75 and that's like 20 seconds there. So yeah, after, okay, to get to negative 100 would probably take another 10 seconds. That's about right. Okay. What will the velocity be after 1 minute? So same trick. What do I convert the minutes to? Seconds. Okay. And I'm solving now for a y value. Okay. So y will equal negative 3.48 times 60 seconds plus 7.75. Okay. So negative 3.48 times 60 plus 7.75. Okay, negative 201.05 meters per second after 60 seconds. Okay, all right, questions on that? Okay, is that making some sense? Okay, I'm going to throw up the other one. Okay, that was also on that quiz. Come on. Okay, did this one give anybody trouble last night? Okay, I'm going to give you about 5 minutes on that one because I don't think we need as much time. When Brooklyn comes back. She comes back, yeah. All right, so let's get going on this one here, guys. Like I say, I'm only going to give you about 5 minutes on this one because I don't think you need much more than that. Okay, so position versus time graph. Okay, basically the flip of the one you had on the quiz. Okay, what's it doing for the first 2 seconds? Nothing. Yeah, it's absolutely nothing. It's just sitting at a position of positive 5 meters. Okay, what does it do between 2 and 5 seconds?
It moves forward.
Moves forward at a constant velocity. Okay, and then it stays put for a couple of seconds, and then what does it do? Goes backwards at a constant velocity, absolutely. Okay, does it go backwards at a pretty high velocity? That line's pretty steep, yeah. Okay, and then we've got stationary again for between 10 and 12 seconds, and then 2 different velocities here at the end, okay, but both in a positive direction. All right, so calculate the displacement between 0 and 10 seconds. All right, I've got a position versus time graph. I have a formula that calculates displacement using position. So that's probably the formula that I should go with. Okay, I don't want to draw shapes here, and here's how I know that, because I've had a few people that are like, oh, which shapes do I draw? On this graph, you don't. Here's how you can check. If I was to calculate the area of, let's say, this box, okay, I'd be multiplying the base in seconds by the height in meters. What's seconds times meters? It's second meters. I don't know what that is. Okay, it's definitely not displacement because displacement's measured in meters. Okay, it works on a velocity time graph because you're multiplying meters per second by seconds, and the seconds cancel, and you're left with meters. Okay, you can always do what we call a unit analysis and see, should I do this here? What units do I get? If they're not the right units, don't do that. Does that sort of make sense? Okay, so I'm not going to do area on this graph. What I am going to do is I'm going to take the final position at 10 seconds, which is -7. And I'm going to subtract the initial position at 0 seconds, +5. All right, -7 minus 5 is -12 meters. That is my displacement. Sorry, that's supposed to be the answer for A. Okay, between 0 and 10 seconds. Everybody all right with what I did there? All right, total distance traveled over the whole trip. Okay, distance is scalar. Okay, I can't do what I did here between 0 and 15 seconds. Okay, because final position minus initial, we changed directions, so I can't do that. Okay, so what I've got to do here is I've got to say, all right, I didn't go anywhere here. And then I went from 5 to 14. 5 to 14 is 9 meters. And then I didn't go anywhere again. And then I went from 14 to -7. Okay, that's 21 meters. Everybody all right with that? I'm just doing those little maths in my head. All right, then I don't go anywhere for a little bit. And then I go from -7 to +3. -7 to +3 is 10, yeah? So that's another 10 meters. All right, so now I know all the numbers that I did there. 9 plus 21 is 30, plus 10 is 40. Okay, so the distance traveled is 40 meters. Okay, just piece by piece, okay, because they did this, and then they did this, and then they did that, and we have to add them all together. Okay, everybody all right with that? That's like saying, you know, here was my house and there was Walmart. Okay, I just did final position minus initial position to find out the straight line to Walmart, but then I couldn't walk straight there, so this is what I did. Okay, just like that question that we did a while back. Okay, trick question. What is the acceleration between, I don't care what the numbers are, what's the acceleration on this graph? Big fat 0. There aren't any curves on this graph. Okay. What's the average velocity over the whole trip? Okay, so I've got a formula on my formula sheet that says that average velocity is displacement divided by time. And I know that displacement can be calculated using position, which I have on this graph, and time, which I have on this graph. So that's a good formula to use. Okay, so I'm going to punch in my numbers here. My final position is +3. My initial position is +5. Okay, and that takes 15 seconds. Well, 3 minus 5 is -2 divided by 15. Is -0.13 meters per second. Everybody all right with that one? Okay, fairly straightforward. Okay, what do we got left here? Okay, so 11, 16. Let's have a look at the first one on the handout. I think that's this one, right? Yeah. Okay, because we haven't done a linear position versus time graph. Okay, we did 2 linear velocity time graphs and 2 irregular position time graphs. Let's look at another linear position time graph. All right, so I'm going to give you a few minutes on this one. Okay, it's the front page of that thing. Go ahead and write all over that. It's yours. Okay, I'll give you a few minutes and then we'll look at that one. All right, guys, let's just quickly walk through this linear position versus time graph here. Okay, so because I have a position versus time graph, I can see that this object, whatever it is changing its position in a forward direction at a pretty constant rate. Would you agree? Okay. When they give me this equation here, okay, where y equals 2.73 times x plus -5.52, they're telling me I can calculate a position, y, because I know the initial position, and if I know the time, x, I would also know this number. So if I'm looking at this, I know that y would be final position. I know that b, the y-intercept, is my initial position. Okay? And I know that x is time. Well, if that's y minus b over x, does that tell me that the slope represents velocity? Okay, that's the process I want you to go through. I don't want you to memorize it. The slope of the graph on the position time graph is velocity. Okay, I want you to be able to figure it out. I want you to look at what do I have? What does each part of that equation I was given represent? Okay, B had to be initial position. Y would have to be final position. X is time. Okay, that means that M has to be equal to V. All right, so that means the velocity of the object is positive 2.73 meters per second. It's the slope of the graph. Okay? Can I use this graph to calculate the position, which would be a y value, after a given amount of time, 39 seconds? 2.73 times 39 plus negative 5.52. Oh, 2.73 times 39 minus, what was it, 5.53? 5.2? Okay, so the position after 39 seconds would be 101, basically, 100.95 meters. Everybody all right with that one? Okay. And then how long will it take to reach a certain position? Okay, well, how long is time? So I'm looking for X, and they gave me something in meters. Meters is on the Y. So I was given Y, I already have B, I already have M, so I should be able to solve for X. So Y equals M times X plus B. Okay, I subtract B over to the other side, divide by M, and I'm solving for X. So that'll be 235 minus negative 5.52 divided by 2.73. All right, that'll tell me how long it takes to get to a position of 235 meters. So 235 minus negative 5.52. Okay, and divide that by 2.73. It's going to take 88.1 seconds. All right. Okay, and what would the displacement of the object be after 20 seconds? All right, so here's a bit of a tricky one. Okay, I know the velocity. It's 2.73 meters per second. That's the slope of the graph. Okay, V equals D over T. Would you agree? Can I just plug 2.73 and 20 seconds into that formula and get the displacement? I can, because it's different than finding the final position. If I do this, if I do y minus, if I do that y equals m times x plus b, okay, I'm finding the final position, not the displacement. Remember, this thing starts behind or below the x-axis. Okay? If I just find the final position, that is not the displacement. I would have to subtract another negative 5.73. I can skip that step by saying I was given the velocity, I was given the time, I want the displacement. That's me, that question is me asking, do you understand the difference between calculating the final position of an object versus its total displacement? Because they are two different things. The only time final position and displacement are equal is if your initial position is 0. Okay, so little trick there, just one of those little things that kind of I want you to think about when you're encountering a graph. Okay, all right, we're going to leave it there. You guys worked really hard today. Thank you. Tomorrow we'll finish off that worksheet. So don't do it at home tonight. We're going to finish that off tomorrow.